26. It's Monday, February 10th. Today's lecture, we're going to continue on probability and statistics by going into hypothesis testing. We've got 3 different lectures that are kind of crammed together. I'm going to do them in separate pieces so that you don't have to watch the whole of one in order to watch the other topics here. But it's basically hypothesis testing, and we have an example of hypothesis testing, and we're going to go into a specific kind called A/B testing that's popularly used these days. Before I dive into that much, though, I do want to go back to Blackboard and point out that we do have a new homework that we posted yesterday, and that is on the data cleaning. So we talked about data cleaning in an earlier lecture, and we took a EDA homework, exploratory data analysis, stripped it down a little bit. There is a IPython notebook file out there, 2 comma separate values files. This IPython notebook is set up to do a load and parse and verification that the iris.csv data set is clean. So your goal is to download this Python notebook. There's instructions in there. It says switch over to use the other CSV file. Try to load it, see what kind of errors you get, and then see if you can fix them. And there's errors in there that are difficult to fix. There's errors in there that are hard to fix. You have to decide what you're going to do with them and fix them. So identifying the errors is the main grading in here, and then the second part. And of course, you can always cheat by comparing the 2 CSV files with each other, but try to do that after you've gone through the stuff, right? So that's not cheating. I posted it out there for anybody to see it, right? Yeah. So that's our homework that we're going to do next. So hypothesis testing. In our outline, of course, we are into the probability and statistics. We're doing hypothesis and A/B testing. Someone cannot hear me. Hang on just a second. Pause. Can other people hear me online? I see there are 4 people online with me. Am I audible? Who can't hear me? Eric, I am not sure what to say. I'm not sure. Okay, you can hear me now. Good. Okay, sorry. Back to the lecture. All right. And you are seeing the slides on screen, right? Everybody's online? Yes, okay, good. All right, so, and then of course, we're gonna go into exploratory data analysis as soon as we finish this and then go through the rest of stuff. Okay, so hypothesis testing. An example, a person is accused of a crime. They stole some cookies from a cookie jar. Yeah, that's it, right? And so they go in front of the judge. And the person is either innocent or guilty, right? And the judge or the jury makes a decision they are innocent or they're guilty. So we have the fact and we have the finding. Now, if the fact and the finding match, the person is innocent, the judge says innocent, the person is guilty, the judge says guilty, we've got no errors. But if the judge says they're guilty when they're not, that's what we call a type 1 error. False positive. You have achieved the criterion we are looking for. Well, you didn't really, right? Then type 2 errors, we say, nah, you're innocent, but they really did it, right? So they're either guilty or not guilty. And of course, depending on the legal system, it's the jury, right? So there's our 4 possible outcomes. No error, type 1, type 2 error. So we've got a null hypothesis, an alternate hypothesis. The null hypothesis is innocent. The alternate hypothesis is guilty in this case, maybe, right? Really, in the judicial system, it kind of predates statistics. It goes way back hundreds of years, and so actually the judicial system has one side says the null hypothesis they're innocent, the other side says the null hypothesis is they're guilty, and they argue in front of the judge and try to convince whatever, So anyhow, the law in theory, innocent until proven guilty, right? Prosecuted hypothesis, guilty, defense, innocent. Whoever argues best wins. Forensic science, get all sorts of stuff in there about why judicial system is not really good science, not really good statistics. So in statistics and science and good medicine and good engineering, the null hypothesis is that nothing unusual is happening, right? Nothing interesting to see here. It's all boring, whatever, the expected thing is happening. Alternate hypothesis is at our chosen significance interval. The data show that something interesting is happening. Causation is likely. Statistics can only give us correlation. It can say these are affiliate, these are associated with each other. They change together. Either one goes up while the other goes down, or they both go up together, or they both go down together, right? But if they're not related, then statistics will tell us there is no. And for some reason decided to stop advancing slides there for a brief second. So we consider the null hypothesis to be true, that is accepted, until we find strong evidence against it. Once we find that sufficient evidence, then we reject the null hypothesis. This implies that we accept the alternate hypothesis. It does not prove the alternate hypothesis. Statistics does not prove things. Statistics is only about showing the likelihood to be high or low, right? Sufficient is defined by our significance level. We've already discussed that. Let's call it alpha. Definition is the probability of a type 1 error. There's another metric called beta. This is the probability of a type 2 error, right? And so we define how much possibility of an error we're likely to accept. In judicial systems, theoretically, we want to have a very low chance of a type 1 error. We don't want to find someone guilty when they're not, right? But that necessarily implies we accept a higher beta error, letting guilty people go, right? One of the things that's obvious about statistics, right? You can't have everything be perfect. Smaller alpha means you have to have more evidence to reject H naught. We compare this with the confidence level, which is simply 1 minus alpha. How confident are we that we found a real effect? There. So, truth about the population, inferential statistics, we've already said. Null hypothesis, that's 1 minus alpha confidence. The type 1 error, that's alpha. Type 2 error is we say they are innocent when they're actually guilty. And no errors when we say they're guilty when they are guilty. The great illustration of type 1 and type 2 errors, the guy comes into the doctor, says, I'm having stomach pains. The doctor says, well, because you're pregnant. That's a type 1 error. Woman comes into the doctor's office, says, I'm here for my 7-month checkup on my pregnancy. And the doctor says, you're not pregnant. That's a beach ball you swallowed. Okay. So, and of course, you're either pregnant or you swallowed a beach ball. Well, how do we know the difference? Well, when you give birth, if we slap and it cries, it's baby. If we slap and it pops, it was a beach ball. Bad jokes. Yes. Okay. Some alpha values. Alpha equals 10%. Says you can expect to be wrong about 1 time in 10. You run the experiment 10 times, you might get it wrong once, right? You run it 100 times, you might get it wrong 10 times, 9 times, 11 times, something like that, right? Wrong here means type 1 error, incorrectly reject the null hypothesis. 90% confidence level is also 1.28 sigma or 1.645 sigma in a normal distribution. We'll see what that means in a bit. Of course, you already probably know that, most of you. 5%, we can expect to be wrong about 1 time in 20. This is actually a medical standard. They have a new drug. They want to find out if it works. They run this thing with an alpha level of 5%. So they can run 200 tests and be wrong 10 times. And I guess that's okay. I don't know. Right. So again, this is 1.645 sigma. That's the same number. Or 1.96 sigma. 1% alpha. 99% confidence interval. We can expect to be wrong about 1 time in 100. Very cautious. This is 2.326 sigma or 2.576 sigma. Choose an alpha level of 50%. We're saying we don't care whether we're right or wrong. We're just flipping a coin. We're going to run the experiment twice. We'll get the answer wrong, about half the time, right? And this is 0 sigma or 6.674 sigma. Alpha equals 0.000006. We are high energy physics in Europe at CERN, and we have a really expensive machine, and we just discovered a new subatomic particle. Yay, the Higgs boson. Okay? So it's weird that physicists have the most stringent confidence intervals, but that's because they got expensive machines and the governments make them use that, right? This is a 99.99994 confidence interval, or 5 sigmas. If you find an error in these numbers, let me know. You might get an extra credit, or you might not. You might just get a dirty look from me for telling me that I made a mistake. It's just some sort of delay. There we go. On advancing the slides. I'm not sure what's up with it. All right, here is our normal distribution. This is not a standard normal. This is just a regular normal because the mean is not 0. Standard normal distribution, the mean is 0. The standard deviation, one standard deviation is at 1, right? So in any case, on this curve, if we start looking at, here's the mean plus 1 standard deviation and minus, plus and minus 2, plus and minus 3. At plus and minus 1 standard deviation, about 2/3 of the data is inside that confidence interval, 1/3 is outside it. So we have basically an alpha level of 32%. Okay. At 2 sigmas, we see 95.45% is in the middle in that confidence interval. And that means we have about a 5% alpha. So, we said 1.96 sigmas. Again, 1.96 is awful close to 2. So that's one of the reasons why that number is, convenient. We do 95% confidence interval because it's about 2 sigmas. If you don't have a computer and the old days, you can eyeball their data, right? Sort of, and then go back and verify whether you're on the right track. 99.73% is within 3 sigmas, right? So that means, less than just 3/4 of 1% is in the alpha range on that. So if we start looking at our alpha values, we said we had 5%. Alpha over 2 is 5%. That means we got 1.65 sigmas over here. So this is a 10% alpha, 90% confidence interval. Here's a 95% confidence interval, 1.96 sigmas inside and 2.5% on the outside. 2.5 plus 2.5 is 5%. That's 95. 100 minus 5 is 95. 99%. Again, we've got 2.58 sigmas around here, and so on and so forth. So that's the relationship between standard deviations and significance levels and confidence intervals, right? So population versus sample is our next thing we need to make sure we understand. We talked about this last lecture. Population is all possible samples, actual voter preferences, all the students at Wichita State, all the people in Kansas, so on, all the zebras on the savannah, all the internet users, right? The sample is a set of specific examples we have to look at. The voters who actually answer the phone when we try to call them and do a poll. The zebras we're able to find in our expedition, our 2-week expedition to the Okavango River Delta during the dry season. The people who actually visit our website, that's our sample. Is our sample always perfect? No. Sometimes our sample can be biased, right? We have to deal with that. We have to understand what it takes to have a non-biased sample. If our website is, something like, oh, I don't want to get too political. I love muskrats. We're only going to get people on that website who love muskrats, right? And that has nothing to do with anybody's name. Pure coincidence. Yeah, there we go. See, I was trying to be like, I picked Musk. Oops. Okay, now we go ahead and wait for the slide to decide it's going to advance now. Done this before. There was something going on, and I forgot what it was. Okay, so the steps to perform hypothesis testing. 1, we set the hypotheses. We have to make sure we have well-written, well-defined hypothesis, null and alternate. 2, we set the significance level. 3, we compute our test statistics. 4, we make a decision. Diagrammatically, here's our population. We set some hypothesis about that population. We set our level of significance. We compute our test statistic based on our p-value of our sample. If our p-value is less than alpha, then we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject. This experiment did not provide evidence against the null hypothesis. Did it provide evidence for the null hypothesis? Well, sort of, a little bit. It's kind of weaker that direction, right? Because, alpha is a pretty small number, so we got a lot of chances to get close to it, right? Here's our acceptance zone. This is a one-tailed test, right? Alpha is a critical region. The p-value, that's the number of sigmas, right, of the median, the mean, where we have our alpha value. If we get a p-value greater than that, we reject the null hypothesis. If we get a p-value over in the acceptance zone, then we accept the null hypothesis. Blah blah blah. What is a p-value? Stands for probability value. How likely is it to see that data that you collected if the null hypothesis is true? The probability of your observation given the null hypothesis. Conditional probability. Right? The likelihood of seeing your statistic under the appropriate statistical test. More detailed, the p-value is likely of seeing a result as extreme or more extreme than the one calculated by your statistical test, assuming the null hypothesis is true. Okay, p-values are most often used by researchers to say whether a certain pattern they've measured is statistically significant. It's just another way of saying p-value is small enough to reject the null hypothesis. It can only tell you whether the null hypothesis is supported or not. It cannot tell you whether your alternate hypothesis is true or why. Right? It doesn't give you any explanation. We could accept a rejection not based on test scores and the critical value. Here's our test scores. Here's the critical value. Look at the numbers don't match, right? But the p-value gives us a single number. It's convenient, shorthand. It's also, some researchers have abused it. They do what's called p-hacking, right? So they go out there and they run the experiment. They get a p-value and they say, okay, I'm going to choose that significance level that makes that p-value, right? Be what I want it to be, right? We can test at any desired level of significance, though. I mean, we can do that. You get a p-value, we say, well, boy, this is we're a lot more confident than we expected. It's a lot smaller p-value, right? We design an experiment expecting a significance of alpha equals 0.05. We get a p-value of 0.004. This is exceeding 99% confidence interval. We're like, wow, that's an extreme statistic, right? So we feel pretty good about ourselves. Of course, we have to run the test more than once to see if that's just an outlier, because outliers happen, right? Directional hypotheses. There are one-tailed and two-tailed hypotheses. A one-tailed hypothesis example is females will score significantly higher than males on IQ score. I should point out that this slide was created by Rosa Saruba, who chose to make females be smarter than males. And based on my experience with my wife, it's true. So, yeah. So our rejection region, here's our critical value. Our null hypothesis is, that there is no difference. Our alternate hypothesis is one-tailed, women are smarter. A two-tailed hypothesis, on the other hand, I was holding his coffee there, is that females score differently. And then we're saying that the distribution of female IQs is maybe a bimodal, or maybe it's not saying bimodal. We're saying it's the mean is either higher or lower. We're just testing if it's different. And so if it comes out significantly lower, we'll say we've rejected the null hypothesis. If it comes out significantly higher, we say we reject. If they don't come out far enough apart, we say we accept the null hypothesis. All right. Now, there are two different kinds of statistical tests, Z or Z, if you prefer, and T. The Z test is a way of testing hypothesis when we already know the population variance. So we know what the difference is. We go out there and measure the heights of the population. We know what the average height of a person in the United States is. We know what the standard deviation is, and so on and so forth, right? That's all public record. Or we don't know the population variance. We're measuring something, how fast do people drive down the street? How much over the speed limit do people drive? What's the average number of miles per hour we exceed the speed limit? We don't know, but we collect a whole bunch of samples of people speeding because everybody does it. So we have a lot of samples. So Z is used to signify normal distribution. That's just a symbol used in statistics to say the normal distribution is a Z distribution. If we have a sample size less than 30, don't know the population variance, we have to go to a T test. What is a t-test? Way of testing a hypothesis. We don't know the population variance, and our sample size is small. Well, obvious. That's the opposite of what we just said, right? Who is student? Student was a fellow named William Gossett. He lived from 1876 to 1937. He worked for Guinness Brewing Company, and they didn't want competitors to know their secret tool for beer quality control. And they had higher quality beer than anybody else, right? They were using statistics. And so we have to say, thank you, beer, for statistics. Actually, William Gossett went down to a local prison, and he measured like thumb lengths or something on prisoners. And he did his paper. He wrote the paper based on predicting something using the length of the thumb of the prisoners. I don't know what the deal was, but anyhow, he had to fake up some research for publication because, again, they didn't want to be able to tell people they were able to test less beer than the competitors in order to get good stuff. So, yeah, I got that. Height and left middle finger lengths. That's right. That finger. See what the correlation was between finger length and your height. Does finger length predict? Other statistical tests exist. Those are Z and T tests are parametric tests. In other words, they assume that the parameters of the underlying distribution can be figured out, that it's a normal distribution, right? There are different distributions. The chi-squared test, right, is used for populations where you don't know what things are. There are other tests that are non-parametric, that don't assume any underlying distribution. An example is the Kolmogorov-Smirnov test. Kolmogorov and Smirnov were Soviet mathematicians. They basically created non-parametric methods in the 1930s. If you get into a situation where you have small sample, you don't know the distribution, you might end up having to do that. Not in this class. But I do have to make a joke here. This is Smirnov with a V, not Smirnov with two Fs. That's the vodka. So no thanks to vodka for statistics. I've got to see how Harika pulls this joke off too. Anyhow, just like to be a little bit interesting, you know. So the t-test, parametric, student t-distribution, population variance unknown, sample size small. Z-test, population variance unknown, or the sample size is large. Again, we use a normal distribution. What's the difference between a t-distribution and a z-distribution? Well, the t-distribution has what's called degrees of freedom. This is the number of variables that are like free to wobble around and still get the same curve, right? Or the same mean, I'm sorry. So a standard normal curve is this green curve at the top. The fewer and fewer degrees of freedom we have, the fewer samples we have in a t-distribution, the shorter the peak, the broader the tails. So basically, the student's t-distribution is simply William Gossett observing that, you know, I can't do full-fledged standard normal tests, but I can get something with a lower confidence with a smaller sample size. And sometimes that confidence is adequate for my experiment. So the t-distribution versus the degrees of freedom related to the sample size is most useful for small sample sizes, as again, where we have to do the t-test. As the sample size increases, t-distribution becomes more and more similar to the normal distribution until by the time we get to 30 samples, it's so close, we might as well just go ahead and use the z-test. What is the degree of freedom? Intuition doesn't explain what that is, because I didn't know what this was for the longest time, and I finally says I'm going to, put this down. So degrees of freedom is defined as n minus 1. I have n samples. The degrees of freedom is 1 less than that. Why? Well, because we want to test if our sample mean is the same as our population mean. So, if we rerun the experiment multiple times, we'll get different data points, right? In order to get that same mean, right, how many data points could have been different? Could have varied. And the answer is all but one of them, because if we move all of them to the right, then our mean moves, right? If we move all but one to the right and that one over to the left, right, then we get the same mean. So that last value is basically constrained by the first n. Otherwise, you would get a different mean. You would get a different result. So that's where we get the notion of degrees of freedom. Imagine we run this experiment 4 times and we get the same mean every time, and we get different values on everything, right? Well, basically what we're saying is that that last value, whatever we collect, has to be a certain number in order to make that mean the same. It's kind of going backwards at it, but that's why we call it freedom, because it's not allowed to move because the other ones are fixed The mean plus the values of the other ones have fixed that last value. Intuition, I don't know if it's helpful. It was for me. It's because, for years I was like, degrees of freedom. Why do they call it that? Right? What's the things that are free, right? So the normal distribution and the t-distribution both have smooth shapes. They're both symmetric. They both have the standard t-distribution has a mean of 0. You can normalize your curve, right? Unlike the normal distribution, we do not assume that the population of variant standard deviation is known. And there's our t with 30 degrees and standard normal. Some sources for this lecture if you want to look at those. And here's a slide that we're going to discuss again in a little bit in the future. But this is important things about how to tell how good your test is. And I'm putting this in here so you have this as a reference in multiple places. Okay. That was hypothesis testing. Let's do an example of hypothesis testing now. First of all, I'm going to stop recording.